Let's learn linear approximations and differentials today. And imagine a curvy road. So I've drawn this graph of y is equal to x square. See, we are seeing a curve here, right? And suppose you're standing at one spot on the road, and if you try to zoom in, and the idea is that this curve almost gonna look like a straight line here. Okay, this almost looks like tangent line, a straight line. Okay. Okay, let me explain more clearly what we are talking about. So suppose we have this function y is equal to f of x, and that function f of x is equal to x square, right? Which means, can I calculate this without calculator? Can you answer this without calculator in simple words? Yeah, sure, why not? It's 100, right? But now if I tell you, can you calculate this without, can you answer this without calculator? Not many of us, maybe one or two, but that's not what we used to, right? So that's the idea behind linear approximations, how to find the value based on what we already know from the closest value to that particular number. So we already know 10 is equal to 100, right? Maybe plug in the value here. But now we want to know 10.1. What does that gives us the value on this graph? For example, this point here where we were standing is at 10 and this is 100. But now we would like to know what is the value here. Okay, not a straight line. So how do we do that? So we already know that the distance between these two, delta x, the difference here is 10.1 minus 10, which is 0.1, correct? So we moved 0.1 from 10 to reach here at 10.1. But now we also need to know how fast this function x square is changing, right? And here comes, we have to take the derivative now to find that, right? The rate of change, how fast is changing the slope. So we all have this function f of x is equal to x squared, and the derivative of that is 2x, correct? At 10, we know that it's changing at a rate of 20. We are trying to find the change from here to here and from here to here, correct? And this is simply just telling us, okay, though this function at 10 is changing at a rate of 20, but if we are moving from 10 to 10.1, this delta x or dx, we have to consider that the change, right? The function, like how this function's output gonna change in consideration to this new point that we are trying to reach. So you have to multiply this with how much we moved from here to here, and this is what gives us dy here. the rate of change multiplied by dx, and which is equal to 2, and this tells you differentials. So differentials, what is differentials are about? Tiny changes. You are moving x a tiny amount, right, from 10 to 10.1, which is dx or delta x. Now differentials, this dy, which is tells us the function's output changes approximately. Is it going to move up or down on this tangent line, and which is how the rate of change at that particular point of what we already know multiply by the change in x, what we are moving, how far we are moving from here to here. So now based on what we already, so we already know that, okay, to reach from 10 to 10.1 we move point 0.1 delta x or dx, right? And now we also know dy, we moved upwards 2 steps or points, let's just say, and we have that value as well. So now how can we put together to find 10.1 square value here? And this is where you can memorize this linearization equation. I mean, we don't have to. I think you pretty much understood what we are talking about. The value of the function at what we already know, right? The starting point plus, let me use different color here. So we have linearization equation which is equal to f of a, the value of the function that we already familiar with, what we already know, where we already standing at 10, plus this dy, the rate of change, how fast it's changing at that known value times the distance we are moving from one point to the other. And here you can put together, right? F of a is what? 100 plus derivative of f of a at 10 is what? It's 20. And dx was 0 0.1. So what we have is 100 plus 2 is equal to 102. 102. Now if you take out your calculator and let's see what value we are getting. 10.1 square is equal to, okay, so from calculator states that 10.1 square is equal to 102.01. So pretty close to what we have found, right? Linear approximation, so you're seeing the benefit now. And now you can also point out that I did not write the linear equation correctly as per the calculus textbook. I was just trying to make it more clear without introducing new variables in it based on what we have already known. So I'll use a different pen to show you. Based off textbook, you can see these two equations. The first is linearization L of x, which is simply f of a plus derivative of f of a times x minus a, which is simply the change from where we already at to where we would like to reach, right? So this would be 10 and this would be 10 point, sorry, this would be 10.1, the new value we are trying to reach, and a is where we already, the value we already know, 10. So this would give you again zero point 0.1, and we call this linearization. And then you would see this another equation, which is that this linear approximation or tangent line, since this is a tangent, right? F of x approximately equal to f of a plus derivative of f of a times x minus a. So why this is still not wrong, because we have noticed that dy is simply this part of the equation, right? And where dx is calculated from x minus a. So it's just an idea. I'm not saying take my word for it, but yeah, if you find the simplification better, but yeah, for sure in exams you might have to, professors would like to see one of these equations being applied, not this would be incorrect. So but in the end it still depicts the same idea, right? So the linearization at point 10.1, which we were just trying to find here, right? At this point, this is going to be f of 10 plus derivative, the rate of change or the slope, multiply by x minus a. So you would still, same thing, right? F of 10 is, you plug in the value into the function. So you plug in the value into the function, f of x is given function x square, and you just plug in here f of 10 square. This is just a recap, which is equal to 100, right? F of 10 is 100 plus the derivative we just found here, which is 2x, and at value f of 10 the derivative is 20, right? Multiply by x is what, 10.1, the point we are trying to find the linearization, and a is 10, known value what we already know, where we already standing at 10. So 100 plus 20 times 0.1, this gives you 102. Since this gives us the approximate value, right? So waste of calculator is 102.01. So we are approximately close, right? We are very close. So I would also use this same thing, right? F of x is what, 10.1. If you same formula here, this is just approximation, and then f of a is again 10 plus, you see the idea, right? So that's what this is all about. And differentials is just basically the tiny changes. You moving, how much you moving here to here horizontally, dx or delta x, and versus how much you moving up or down vertically, which gives us dy. And make sure you know that delta y is not same as dy. Delta x or dy or dx, yeah, it's the same thing. It's just telling us how much we have moved horizontally from one to the other point, the distance. And but change delta y is not the same as dy, as dy gives us the rate of change multiplied by the distance we moved, and delta y is actual change, whereas dy is the approximate change. Approximate change, which we are just calculating based off the slope times the change, horizontal change in x, and this would gives us the function's output change approximated, right? But this delta y is simply telling us the actual change, which is function x, what we already know, plus the move we are making from here to here, the distance delta x minus f of x, which is, if you're trying to find the delta y here, what is that? So f of x is 10 plus the change is 0 0.1, right, minus the function value at x is f of 10, the known value. And don't get confused here, right? This is simply this is based off the textbook, and don't get confused. This is basically the textbook definition of delta y, which is still applies here, right? Suppose we are using a, right, instead of stating x, and we are stating x as the unknown value here, and this is still the change we are moving, and f of a, and stay same thing, right? But now the thing is, since delta y is the actual change, that means the actual value of this function of 10.1 is 102.01 minus, and the actual value of f of 10, which is correct, is 100. So this delta y is equal to 2.01, whereas this the dy, which is the approximate change, which is equal to 2, that we have calculated based off the slope times the dx. And yeah, so just keep in mind that delta y is not the same as dy, whereas delta x and dx is the same thing, the distance we're moving here on the graph. So I hope this all helps, and forgive me if I wasn't any help. Thanks so much for watching.